Good morning, everyone. Thank you for joining for this distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Mohammed Sakib Hasan. His title of the talk today is Security Applications of Discrete Time Chaotic Systems, Recent Work, Challenges, and Opportunities. Dr. Hasan joined the Department of Electrical and Computer Engineering in University of Mississippi as an assistant professor in fall 2019. He received his B.Sc in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology in Dhaka in 2009 and Ph.D. degree in Electrical Engineering from University of Tennessee, Knoxville. His research interests include secure nanoelectronic circuit design, nonlinear dynamics, and chaos, neuromorphic computing, semiconductor device modeling, and VLSI circuit design. Dr. Sakib, thank you so much for agreeing to do this talk. It's a great honor for having you as part of the webinar series. The floor is yours.
Thank you so much for this kind introduction. So should I turn on my video?
It's up to you, and depending on...
Because I want to share the slides.
Yeah, you should be able to share the screen.
When I try to start the video, it says that you cannot start your video because the host has stopped it.
Okay, Jamison, do you know what's going
on? Not entirely sure what that could be. There, it looks like it's loading. Yep, I can see your screen.
Okay, so I think you cannot see me because the video is off, but can everyone see my slides?
Yeah, we can see your slides. That's fine. Yeah, if you can make it full screen, I think it's not in a full screen mode.
Right. Yeah. So can you see the full screen now?
Yes.
Oh, okay, that's great. So thank you. Thank you so much for this kind introduction and the invitation, the opportunity to talk about this. So the title of my talk is basically Design and Application of Discrete Time Chaotic System, and with like the reference to these things like recent trends, challenges, and opportunity. I did not want to put too many things in the title, but basically it's part of the distinguished webinar series in artificial intelligence and cybersecurity. So basically, a little bit of background. So I am now at Ole Miss, University of Mississippi. I'm an assistant professor. I joined in 2019. So in this presentation, I know it's a 1 hour time. So I had one question. So is it 1 hour for my talk and question and answer is separate, or is the whole thing 1 hour?
It's about 50 minutes of talk, 10 minutes of Q&A.
Perfect. Thank you. So my presentation is, so I'll try to stick to 50 minutes. So my presentation layout is basically motivation, why we are doing this. Then I will introduce my main thing, like discrete time chaotic system. I'll go over some of the recent works that we have been doing, and then I'll probably shed light on some of the other things that other people are doing if time permits. But then I will talk about the main, like the opportunities that are there and what are the challenges that we are facing. And finally, I will conclude my talk with my overall vision on this field, like what I think should be done and basically what are the what to take away from the audience. However, one thing I need to mention that because of the constraints of the time, I will not be able to go over all the details of these topics because these are kind of involved actually. And when I started doing this, I had the same problem. So it took me a few months just to get used to nonlinear dynamic system and chaos theory. So when I gave previous talks, the problem that I faced was that like the feedback that I got is that it becomes difficult to follow if I go into the details within the 50 minutes time. So I have a few previous talks. They're already there, so I don't want to repeat those. And also, like we have quite a few papers by now. So we have 23 peer-reviewed publications in the last 6 years on this field. So a lot of the details can be found there. So what I would suggest my audience to do is to take this more of as a podcast. So even if you can't follow everything in the slides, that's okay. The only reason I'm putting so much information in the slides, and I have quite a few slides, like I think more than 80. Of course, I'm not going to go over each of the slides in any detail in 50 minutes. That's not possible. The only reason is that I was told that the organizers are going to upload this in YouTube, and I will send the slides to the organizer after the talk, so they can put this in the YouTube in the description. So the information will be out there. So the reader or the audience, if they're interested to further pursue this, they can go back and watch the video and follow the description and the slides, and they will have links to all the detailed information if they want to pursue this. So that's why I'm putting so much information in the slides. But if you having difficulty following the slides, that's bound to happen. So don't worry. Just take this as a podcast, and I'm going to give the big picture and try to follow along. Okay, so with that being said, let me introduce what I'm doing this. So the main motivation is that security for edge computing. So as you guys all know, that Internet of Things has become a huge thing nowadays, and we expect to have like Internet of trillion intelligent things in the coming decades. And it has so many applications that I'm not going to bore you with that. But there is a fundamental problem is that previously when we started developing computing in the early 1940s and 1950s, the main focus was computing, like how performance of the computing systems. So how fast you can make it. But in recent times, in last 20 years, two other very important things have become apparent that we cannot ignore that. And they are energy and security. So these are two things that I'm very focused on. So I also do neuromorphic computing where I focus on the energy aspect, and I do chaos-based security stuff. So I think in modern days, my motivation is that if we want to do some of these things, we cannot ignore security anymore. And traditionally, security has been kind of like an afterthought, So this time around, when you are building these things, I personally think that we have to change our paradigm a little bit. So we have to have our computing stacks previously was kind of separated, like from device, circuits, algorithm, architecture. They are kind of separated and people work on their own fields. I think it has to be vertically integrated, and security has to be a part of the full stack. That's a difficult challenge because on the other hand, we have now energy constraints, right? We are consuming too much energy, especially with the big data and AI explosion. So somehow we have to reduce our energy, yet introduce more features as far as security is concerned. So that's a hard challenge. And one interesting thing that has emerged in the last 20 years. So traditionally, security has been mostly software level security, like cyber security and stuff. They focus on more software level solutions. In the last 20 years, there has been a massive boom. I think like a lot of interest. People are realizing that ultimately systems run on a real hardware. There is the underlying physical substrate where computation is being done, and you cannot ignore that. There have been some serious security threats like Spectra and Meltdown and all that. So people realize now that there are side channel attacks. So people are really taking this seriously. And also there is opportunities there. So you can actually, the actual hardware, the physical device and CMOS, traditional CMOS and also emerging device, you can leverage their power to provide a security solution. So my background is from VLSI. So I did device modeling and circuit design as my Ph.D. So I worked with the emerging transistor and then moved on to other emerging devices like memristors and so forth in my postdoc. So based on that experience, I think that this fundamentally irreconcilable difference between energy and security and as well as keeping the performance, we have to change our paradigm because of Moore's law is slowing down, Dennard scaling is long dead. So we need to change the paradigm, and that's why I'm looking into like more a different outlook on the security solution. One of them is nonlinear dynamics and chaos, and for that, like the problems that I'm trying to solve, here you can see this. So basically you need low area, low power and low latency. Something that can be very useful is unclonable physical design, I think. And you have to have high security with limited physical entropy. And this is where my research comes on, the chaos generating analog discrete time circuits. I should mention that I also do chaos generating digital discrete time circuits, but for the sake of time, I'm going to confine to my analog part, which I think is more novel and more interesting. So what are the like basic features? So chaotic systems are unpredictable in a sense that it has infinite periods, so it never repeats itself. the finding pattern is difficult. Our analog implementation is very different than conventional approach. It's a graphical approach. Only very few groups, I think, has worked on this. So, so it is relatively like there is a lot to explore there, I think. So there is a low transistor count. So it's like perfect for edge computing. It's flexible. It's not just flexible. It's actually flexible and reconfigurable at the same time. I'm going to explain what I mean by this later. And then there is the butterfly effect. So you probably have heard about butterfly effect. So it pertains to the sensitivity of the chaotic system. So what is chaos? So there are three main things to remember about chaos. So it's a special phenomenon in a nonlinear dynamic system. So if a system is nonlinear, some sort of nonlinearity, maybe very small, like a square or cube, just a quadratic or cubic nonlinearity. Even then, it can happen. It has to be a dynamic system, so it changes in time. It is a deterministic system. So everything is known, right? So you know the initial condition, you know the differential equations. Still, it seems unpredictable. So that's kind of seems self-contradictory, but we will see what you mean by it. And it has sensitive dependence on initial conditions. So this is the famous butterfly effect. There are movies named after this. It was in Jurassic Park movie, the famous movie Jurassic Park. There was a chaos theorist who was exploring. Jeff Goldblum played that role. So early 90s, the people are very interested in these things. And the work that we have been doing is mainly on the right-hand side, you can see scroll if you follow my cursor. So let me put the laser point. So what you can see here is that it seems like this is the trajectory of a chaotic system. So this is a famous chaotic system, by the way. This is the one that started it all. In 1963, Ed Lawrence from MIT reported a chaotic system for the first time by numerical simulation, because you have to do numerical simulation because nonlinear dynamic system does not have any analytical solution. So before the advent of computers, it was not possible to solve full details of things. There was a very interesting theoretical work, but computer actually made this possible. So Ed Lawrence 1963 reported this thing. And what we are trying to get here is that, and we have shown in the last, I've been working on this for like 6.5 years, and we have explored quite a few applications. So they range from RNG, random number generator. We have tried both. We have done both TRNG and PRNG, and I'll talk about it. And then we have Parks. So Parks is a physically unclonable, reconfigurable computing system. So it's similar to a PUF. So it has the PUF property, which is physically unclonable function, which can be used for authentication and encryption, and quite a few applications people have been exploring. So it has PUF, but it's also a reconfigurable computing system. So it can be used for logic locking. So that's the third application. So logic obfuscation and logic locking. So that can be done. And PUF can be used for authentication as well. So that will be another security application. There is a few other security applications. So one famous one is encryption, chaos-based image encryption. So we are also working on that, but that's on the digital front. Analog circuit has still, we have not matured it as much to do encryption real like precision. So for the encryption work, we are still doing on the digital front. So there is other works on secure computing, secure communication, on chaos-based secure communication. We have not yet delved into that. There is also famous works, like very important, interesting works on neural network, chaotic neural network. So basically, human brain is a connection of neurons with synapses, but it's a nonlinear dynamic system, not the feed-forward artificial neural network that we usually see. Actual neurons have recurrent connection, so it's a nonlinear dynamic system. And chaos has been shown, like there has been a chaotic neural network work, HofFieldNet, very interesting field of research there as well. So I have done a little bit on that. So how we can do stochastic neural network using chaotic unpredictability, but there is a lot more to explore there as well. So in summary, like based on this fundamental idea, you can have very interesting applications. So let me go to the origin story a little bit. So I could not help putting this in the slide. So this is the seminal work by Ed Lawrence. So this is the origin, like the three equations. As you can see, it's a very simple equation actually, like three ODE and three state variables X, Y, and Z. The amount of nonlinearity is very minimal, to be honest. So there is this XZ nonlinearity, and there is this XY nonlinearity, and that's it. And that was enough to create a system that has very interesting dynamics. So this is the original screenshot from the original paper. And this is kind of a modern day animation that you guys, people see. So why is this is interesting? Just to give a summary, the math is a bit involved, but if you have a 2D plane, let's say, and you have a point in the 2D plane, it's a dynamic system. So it's moving around in this 2D plane. At some point, if you are an energy bound system, you cannot go infinity, right? So you have to go back to the original value sometimes. And if you go back to the original value, it's the same differential equation, same initial condition. So you are bound to repeat itself. So it will become a periodic thing. And that's why I think most people never realize that this can happen, that you can have a periodicity out of this kind of deterministic system with butterfly effect. Because first of all, there is no computer. And then the second thing is that like it's really unintuitive. But if you have add third dimension, like if you just have add a third dimension, in a three-dimensional system, actually you can always oscillate with never intersecting the original point, never coming back to the initial condition, and you keep doing this. So it looks like it is repeating itself in some sort, but it never really returns to the original condition. So it never repeats itself. It keeps going back and forth like this. So you need at least the third dimension. So that was the big invention, is that chaos can only occur on a continuous time dynamic system if you have three or more dimensions. Okay. Now, one thing I would mention that though it started in 1963, like the modern way of looking at chaos, it has a rich historical tradition, go way back to the Newtonian dynamics. So what do I mean by that? So when Newton was coming up with law of gravity, the thing was that you have two body problem. So you probably have heard about the three body problem, which is a very famous problem in mathematics. Actually, that is how chaos started. So two body problem means that sun and earth, and Newton wrote his laws of motion. You will solve it, perfect. You can find out how earth moves around the sun. But then Newton tried to solve it by adding a third body, which was the moon, basically. So he called it the problem of the moon. But so sun, earth, and the moon. Surprisingly, only three bodies. If you write the equations, it becomes nonlinear differential equation. And it's a surprisingly difficult question, and it bugged Newton until his death. It took 150 more years until the coming of another famous French mathematician and physicist, Henri Poincaré, who worked on the three-body problem and made important advancement. So he showed why this is a difficult problem and why there is no solution and what can happen. The problem was that mathematicians want to work with analytical things, like something close form analytical solution. Poincaré, like he was such a visionary that without any computer or anything, he had this imagination. So in his mind, he could see the geometry of the space. And based on this geometric approach, he developed a theory and kind of showed that. Unfortunately, mathematicians were interested in this, but the scientific and engineering community, I think, did not pay too much attention until 1963. When Lorentz actually showed with a computer that this can happen. People thought that it was a numerical error, by the way. So people thought that it's a numerical error. Yeah, computers are digitals, they are truncation error. And that's why this is happening. So Lorentz keep repeating his experiment with the newly bought computers in MIT. So only few universities have computer back then. So he kept repeating this and showed that no, it's a rigorous thing. It's actually happening. So that's kind of the background. The reason I'm putting the background is going to be linked with my overall theme of my talk. Is that I think like the main problem why there is not enough attention, in my view, in this field is that there are certain complication with analyzing nonlinear dynamic system that people want to avoid it. So that's why it took so long. So I always wondered, like, how can it be that it's such a simple three differential equation? How can it take until 1963 to come up with this? We have already done theory of relativity, quantum mechanics, and like all these great advancement. And how can it take 1963? Because I think some of that has to do with the difficulty of analyzing nonlinear dynamic system. And that's also related to what we are trying to do. So we are trying to take this theory and put it in engineering application. But I think more awareness of nonlinear dynamics is necessary so that students, even in the undergraduate curriculum, where we mostly focus on linear systems, maybe introducing a little bit of nonlinear dynamic system, like simple systems like Lorentz system or logistic map, might be a good thing moving forward if we really want to harness all the powers that are interesting dynamics that in the nonlinear. So with that motivation, let me go to my research. So I don't do continuous time chaotic systems because they are difficult to implement in hardware. I'm more on application hardware kind of coming at it from that perspective. So there is a discrete time version of this, which is called discrete time chaotic system. And there are some famous examples, logistics, sine and 10. The advantage of this is that in continuous time, as I explained, you need at least 3 dimensions, 3 variables. In discrete time, you can have 1 variable and still have chaos. So the circuit implementation is much simpler. Also, you don't have to solve a differential equation. So in discrete time, differential equations becomes difference equations. So it's an iterative map. So let's look at the most famous one called the logistic map. So you can see the equation here. So xn plus 1 is a function of xn. So it starts from n is equal to 0 and then keep repeating this iteration and you have the chaotic dynamics for certain values of the parameter, which is shown here with the value c. And similarly, there are other famous maps like sine map, tent map, Gaussian map, Bernoulli map. So we explored that in our digital research. And this is what the transfer curves looks like. The main takeaway from this transfer curve is that you need to have 2 slopes, one rising slope, one falling slope in these maps. You can see, basically you need to have a non-monotonic transfer curve. So having just a nonlinearity is not enough. So if you have e to the power x, it's highly nonlinear, but that's not enough because it's still monotonic. So you need to have non-monotonic. So for people who are coming from circuits, like you need to have some sort of NDR kind of thing, negative differential resistance. Okay, so basically this is there. This is all good. People have been doing this for a while. It's simple equations. You can implement that in hardware, digital systems like FPGA or ASIC. You write a very low code and implement that. That's good. What happens? What happens is that there is a parameter C, and if we keep changing these parameters, the dynamic of the system change. And by dynamics, I mean that how X varies with N, right? So the conventional way of doing this is called bifurcation diagram. So these 3 plots in the below, if you follow my cursor, are the bifurcation diagrams. So in bifurcation diagram, what we have is that each value of C, we plot steady state values, preferably very long sequence. So let's say 14,000 values, what we do in our lab. So you keep iterating this map for 14,000 iteration or 15,000 iteration and plot all the steady state values. So you truncate the initial transient, like first 1,000 values, and then plot the remaining 14,000 values in the y-axis. Now, it might look like that this is just a single point, if you follow my cursor, but it's not. It's actually 14,000 points superimposed on each other. So in a steady state, things have converged to a single value, this dynamic system. And this is called, in the dynamic lingo, this is called a fixed point. So things are very boring. The C is changing initially. The fixed point was 0. Then it keeps changing, but it's still a fixed point until it hits 0.75. At that point, a very interesting thing occurs. So a single fixed point becomes a periodic sequence. So basically, the 14,000 values that we are plotting, 7,000 of them in the lower lobe and the 7,000 of them in the upper lobe. So it's just keep oscillating, but it's a periodic oscillation, period of 2. But then the magic happens is that after a little bit of time, that period of 1, period of 2 becomes a period of 4. So that's why this is called bifurcation diagram. So 1 becomes 2, and then each of them becomes 2 again. So 2 becomes 4, and then 4 becomes 8, and then 8 becomes 16, and it happens exponentially faster. So this is what was discovered, and there is a famous seminal work, which kind of is the basis of my analog research as well, is the Feigenbaum's 1978 papers. And going back to the motivation, I think, this is also confusing because the seminal works in chaos became famous only 10, 15 years later. Initially, none of them was published. So in 1963, when Ed Lawrence submitted his paper, nobody published it. And after, I think, years of like frustration, he published it in an obscure journal of atmospheric sciences. And later, people kind of realized the significance. Similarly, Feigenbaum's 1978 paper is one of the seminal works of the last century. He found how apparently different mathematical maps have similar dynamics and the fundamental theory behind it. Nobody published it for a few years. Again, an obscure journal in 1978. And after a few years, people kind of, mathematicians and the physics community really took it and became very prominent. So, like Feigenbaum's insight was that, yes, the math looks different, logistic, sign, and there are thousands others. However, they all have the same property, is that 1 becomes 2, 2 becomes 4, and 4 becomes 8. And not just that, the rate becomes exponentially faster. So if you can see here, 1 becomes 2 here. This is the, if you take the distance between the first bifurcation and the second bifurcation, and then take the distance between second and third and fourth, you will see that this distance is becoming smaller and smaller. It's more evident here in the 10th map case. So you can see here that this distance and the next distance is smaller. The next distance is even smaller. And not just that, it exponentially shrinks, and the ratio is always a constant. Its value is, I think, 4.88, something like that. And it doesn't matter, like which mathematical map you work. This is the astonishing discovery, that like whatever map you're working on, as long as it has this non-monotonic property, and it always has the same ratio between bifurcations. And this is considered one of the fundamental constants of nature. Nobody knows why it is there, but it's a fundamental constant, like pi. Like it's always there. Like which map, the bifurcation ratio is always the same. So this is how things have been mostly done in this field. Okay, so you have mathematical equation, you work on that, improve them a little bit for application. So I do that for my digital work and implement that in FPGA or SE. Okay. So this chaotic part, we done this, we have implemented in Verilog, we have done ASIC. Actually, we just got our first chip back yesterday. So I'm very excited about it. But the problem is of this digital approach is that if you just do 32-bit logistic map, this is what it takes. Now, why is that? So why do you need to, you can say that, why do you need to do 32-bit, right? Why don't do 8-bit? Well, you can't. Or at least, I mean, you will not get the advantages. Because, so this is another very subtle point, is that this is the deterministic system. So if you implement this in a digital implementation, then if it has n bits, then the state space is 2 to the power n. And it has to traverse through all of this state. And if it comes back to the original point, it has to repeat itself. There is no other way. So it will bound to be periodic, and the period is going to be very small. So it will not be good for security. So to okay, so that's the bind that we are in. So the reason what we are trying to do is going into analog style. Now, analog circuit has been done with chaos. So logistic and all have been done with analog circuit. So you take the equations, you implement that in analog circuit with analog signal processing techniques. But those circuits are also bulky, like you need current sources and it's complex. So what we have found out there is a very interesting work in 2003 by Dudek and others, where they showed that, hey, why we are trying to take a mathematical equation and implement them in hardware? Why don't we take the basic insight? Is that all you need is a non-monotonic transfer. But transistors are nonlinear, right? they are not just zeros and ones like in a digital switch. They are actually, their transfer characteristics is very nonlinear. So why don't we take the CMOS transistors and build a very simple analog circuit? So just to give, just to put things in perspective, so you see here, like it's a 3 transistor circuit. It has a transfer curve which looks like this. So the inside is actually like strikingly simple. Is that I need 2 slopes. So one rising slope, one falling slope. So if you look closely into this circuit, you will see that there is a source follower and there is a common source amplifier. Very well-known undergraduate circuits. And one of these transistor is doing kind of double dipping. So it is part of both circuits. Common source follower, and one case it is a load, one case it is the amplifier. So you have 2 slopes now. And surprisingly enough, that's good enough, actually, because they're Feigenbaum's original insight that it actually does not matter. The math does not matter. It's a graphical geometrical approach that as long as it has that kind of transfer curve, you will get chaos. And yeah, indeed, you get that. So so if you do the simulation, I'm not going to go into the details for the sake of time. So you will find out that for certain value of the parameter, you do get a chaotic circuit. So just to give an example, so when VC is 0.9 volt, the sequence is aperiodic. And not just that, it is very sensitive to initial condition. So we start with a tiny difference in the initial condition. The sequence looks same until the step 2025. It starts diverging. And after a while, the 2 sequences become almost like orthogonal, like unrecognizable to each other. Okay, so that's kind of the background of our work, and we have been working on this. So from now on, all the details of the work, I am going to just summarize and go very briefly. So don't bother with the slides details at all. So just follow what I'm trying to say. So this is the bifurcation diagram, and this deep blue portion is the chaotic region. So you see initially dynamics is simple, then things become chaotic, and we can use that. So that's kind of the basic idea. And there are measures to do this. So there have been a lot of theory developed by mathematicians and physicists about how to measure chaotic system. So we do quite a few of them, but for the sake of time, just focus on one, the fundamental one, which is Lyapunov exponent. So it captures, so the equations is giving here, but basically in plain terms, if you start from initial condition, if you slightly change it, how sensitive is that? It is trying to capture that. So if Lyapunov exponent is positive, it is chaotic. If it is negative, it is non-chaotic. Even if it is positive, it is chaotic. But how chaotic it is? Like how much chaotic unpredictability can you harness? So the more Lyapunov exponent or the higher Lyapunov exponent, the higher the chaos, basically. So it's a good quantitative measure of the system. So that's why we use Lyapunov exponent to measure our system. So as you can see, that initially until 0 to 0.5, things are simple, no chaos, and Lyapunov exponent is, negative as we expect. And then when things become chaotic, Lyapunov exponent is positive. And when things are really chaotic, the values are higher. When things are not that chaotic, things are a little lower. So we know which point to select based on Lyapunov exponent. We ideally want to have higher value of Lyapunov exponent, right? Basically. And what is the ideal case? Well, you can theoretically prove that for a one-dimensional map with only 2 slope. So in other words, if you have, let me show what I mean by this. So for a circuit like this, so you have 2 slopes. The highest you can get out of this is 0.693. So that's our aspiration, right? So we are going for 0.693 is the ideal value of this kind of map. Where we are around 0.3, 0.32. So that's not that great, But this is the initial exploration. So you have a circuit, you have 0.32. And Lyapunov exponent is actually in the log scale. So there is a lot of room for improvement from 0.32 to 0.693. And 0.693 comes from the fact that it's ln of 2. So that's why. Okay. So, and then there is another quantitative measure is correlation coefficient. Again, I'm not going to bore you with the details of this. So basically, if you start from 2 slightly different initial conditions, the results will be drastically different. So the correlation is 0. So that's what we show in our exploration that, yeah, it does actually show that there is no correlation with slightly different initial value. Okay. So This butterfly effect has been explored a lot. So I am now going to very quickly go over the slides. So don't bother about them. So Kolmogorov entropy, correlation dimension, these are all coming from nonlinear dynamics system theory. And we use them in that. So you can check our papers for that. I'm going to give a list of all our papers so that you can go back and check. But now going to the main thing is that the 1D maps has some limitation, and we are trying to go. So it has limited chaotic range and performance is not robust. So what we are trying to do, so let me give graphically. So you see the parameter space is 0 to 1, but only a subsection is chaotic. And even then, the performance is not optimal. It's around 0.32. We can go up to 0.693. So there is a lot of improvement. So two main dimensions of improvement is how to put this. So quality and quantity. So we want more quantity of chaos and more quality of chaos. So in other words, so you can see in the Lyapunov exponent plot. Let me go back. Yeah. So some portion of this thing, parameter space, is non-chaotic. So we are missing that. And even things where things are chaotic, we are not hitting the height. So we want to improve the width and we also improve the height. Width is kind of the quantity and height is kind of the quality. So main task what I've been trying to do is that trying to come up with analog circuits. So I had some background in that. So analog circuit design, CMOS transistor. How can you kind of come up with simple circuits that can be used for edge computing, has great quality of chaos, high Lyapunov exponent, and great quantity of chaos. So that is what I'm going to discuss now. Okay, so the first technique that we explored is from the digital domain. There have been research was dynamic parameter control. So we took that idea and tried to implement that in analog circuit. The main idea is that instead of one map, you will have two maps. The first map output is going to modify the second map's control parameter. As a result, we get dynamic parameter control. Don't worry too much about it. It's basically double the cost, better the performance. And does it actually happen? Yes, it does. So as you can see, the original circuit was in my left, my cursor, and it has very limited chaotic window. And my current circuit has almost 100%. We call it chaotic ratio in our group. So like going from 20% to 100%. So the quantity of chaos has improved by this. Okay, and looking at the Lyapunov exponent, has it improved? The quality of the chaos? Unfortunately, it has not. So the original values was around 0.32. These values are also around the same ballpark. So this improves with the chaotic window, but not the quality. Okay, so how can we improve that? So again, from the discrete time literature, we found out that from the digital domain, people have been doing cascaded chaotic map. So the idea is very simple. So you put two of the maps in series, and as a result, you get higher nonlinearity and Lyapunov exponent improves. So we tried to implement that with our CMOS systems, and indeed it does. So we get theoretically, so we developed some theoretical limits. So under certain constraint, you can actually double the Lyapunov exponent. So you can go from 0.3 to 0.6, basically. So we showed that. So then by this way, we can hit the limit, so 0.693. That was the original limit. So you can even go beyond that. So if you put three of them, you'll get 0.9, right? But you're kind of cheating because you are using two maps or three maps or multiple maps. The real challenge is how can you do single map and make it 0.693. But this is the good solution, right? So again, the same problem that you double the cost and get some performance out. No, that's not a bad bargain because each of these maps are very simple, 3 transistors. So even if you put 2 of them together, it's only 6 transistors. So which is like I counted the number of transistors you need for the digital thing. So you need at least 100,000 transistors. I mean, of course, we have very tiny transistors, so but still it's a lot. So 100,006, not a bad bargain, I would like to think. Of course, the analog transistors are a little bigger, but let's say 6 becomes 60. Even then, it's a pretty good bargain compared to 100,000. So that was the 2 solutions that we really explored and showed some solution on that domain. And then we showed an application and random number generator. So I'm not going to discuss the topology, but we came up with a comparator-based topology for this, and we generated a sequence. It's a pseudo-random because it's a deterministic system. Chaos is a deterministic system, and we proved the randomness using statistical tests. Like there are tests NIST, test U10, what are the other, diehard. So we passed all the tests. So it seems like a very promising tool, very compact. We showed the overhead comparison and all. So that's the application that we saw. But there is a very interesting implication of this. So we are running simulation using Cadence tool. And we are doing a nominal simulation. Yes, in the nominal simulation, it's a PRNG. But in real life, in analog circuit, if you actually build the chip, there will be process variation, die to die. There will be also local intra-die variation. So chip to chip variation, and also inside the same chip, different circuits will have slight differences. Supply voltage variation, and also temperature variation. So this is called the PVD variation in the VLSI world. So that means that even if you build the same chip twice and give the same initial condition, it will not produce the exact same output. So in ideal simulation that we are running, it's a PRNG, but in actual world, it will be a TRNG. So that's our thing, at least in the long term. So the actual sequence that you will get, binary sequence you will get, will not be the same. Each time you run the same thing with the same initial condition, same seed basically in the random number, it will generate a different sequence, right? So that's what we are kind of exploring, and preferably if you can build actual chip and demonstrate that there will be gate. We need some funding for that, but chip fabrication takes money, but we are working on it. So that's basically one application of this. Then we improve the parameter modulation technique. So previously parameter modulation was done with a linear combination, linear equation, and you can do that with a bunch of amplifiers. But then it added overhead. So we also wanted to replace this amplifier circuit with a simple 2 or 3 transistor circuit. Again, a nonlinear transformation instead of a linear transformation. So we came up with a nonlinear circuit to do that. And again, you see, it's a pretty simple circuit, actually, 5 transistors. And this circuit has very good properties. It has all the same advantages, but with much less overhead. So because we are kind of targeting edge devices, so that's why we're so concerned about overhead. Okay, so I'm not going to discuss the details, but it has better properties and less overhead. So that's one approach that we did. And then we came up with this idea of self-parameterization. So dynamic parameter modulation means that you have 2 maps, right? So you have double the cost. Can we do self-parameterization? So the map itself reconfigures itself based on its previous output. So then you don't need the second, the second, like one seed map, one control map, you combine them into a single. So we implemented that. This time around, we tried to first develop the theory. So we started with mathematical equation, logistic map, tent map, and sign map. So we like 3 representative maps. So we developed the theory in the math domain and implemented it in FPGA. But we also extended this work to a, so this is the FPGA implementation, the digital result. But we also extended this with the analog circuits. So we proposed 3 new analog circuits, which can do this thing. So as you can see, the performance are pretty good. So the original circuit was chaotic only over a limited time window, the deep blue region. But then the new circuit is red all over the place. So it's chaotic, 100% chaotic across the parameter space. And we similarly show an application in random number generator, and we proposed a different topology. It's a ADC-based topology, 4-bit ADC-based topology instead of a comparator-based topology. Okay, so it passed the test and all that. And then we thought that, okay, 1D chaotic system is great, but its dynamics, it does not capture the full complexity of the nonlinear dynamics. So if you go to higher dimension, you get more interesting nonlinear dynamics. Security is an arms race. So of course, the attackers are going to break our system. So if you have a 1D system, because its dynamics is less complex, attackers can break it at a certain point. So we should have a methodology that if that is the case, then how can we make it more complex for the attackers? And that method is going from 1D to ND, so arbitrary higher dimensional system. So to our knowledge, nobody has done this using this graphical approach so far in the analog domain. So I think this is the first work on this thing that we reported last year. So we came up with so original implementation of multi-D systems are huge, as you can see here, like people, the digital way of doing things or analog way of doing things with self-components, off-the-shelf component. So our graphical approach is different. Again, we just look at the geometrical state response, and based on that, we do use our analog circuit design knowledge to come up with a circuit. So you have two maps, seed map X and seed map Y. Seed map X modulates the control parameter of Y. Seed map Y modulates the control parameter of X, and that's it. Because we already can characterize X and Y, we know which parameter space is chaotic, right? Let's say between 0.5 and 0.7, things are chaotic. So we just make sure that our nonlinear transformation always projects into that chaotic region. So we are kind of forcing both of them to be chaotic on the same place. And if two things are coupled and both of them are chaotic, then the whole system has to be chaotic. And there will be a 2D chaotic system. That was our hypothesis, that, well, it should work. And luckily for us, it did. It actually worked. So this simple scheme worked. So we have chaotic system. We propose 3 topologies based on, so our theme was that we want to make a general approach. So we roughly categorized 1D systems into 3 types: left bifurcation, middle bifurcation, right bifurcation. And we propose circuit so that you can work with any 3 of them, So we provided 3 solutions for this series. And all 3 systems are very chaotic, robust chaos in technical term. So 100% chaos across the parameter space. So it's a 2D system. The analysis is much more complicated, Lyapunov exponent and coefficient correlation and everything. But we did that, and all those things kind of passed through, performing well. And if you look at the Lyapunov exponent, there are actually, in 2D systems, there are 2 Lyapunov exponent. The first Lyapunov exponent tells you the maximum Lyapunov exponent is the main Lyapunov exponent. So there is the interesting things in 2D, in multi-D, is that if you have n-dimensional system, you have n Lyapunov exponent. The first one is the highest one, tells you whether chaotic or not. But if both of them are positive Lyapunov exponent, it's called hyperchaos. Hyperchaos means that the state is diverging in both dimensions. And you can extend this definition to 3 and higher dimensions. Anyway, the main point is that we did not actually thought this is we did not plan for this. It surprised us. We just expected chaos. We did not expect hyperchaos. But it turns out that some of our designs, at least around certain parameter range, is actually hyperchaotic. Not just chaotic. So that seems to be very promising, because hyperchaos has a lot of interesting dynamics that can be used. So we are now looking into it. And there is an analytical method, like how do we use that stability of fixed points and all this. So this is coming from mathematical theory of chaos and dynamic system. So we kind of use that to build our intuition as an analog circuit designer, how to do this. And I'm not going to, for the sake of time, I'm not going to go over that. So let me just go to the main topic. So I think based on that, we did a lot of new other circuit topology, which are detailed in this, described in details in the following slides. But a lot of applications that we have covered so far in the last 6 years. I am just going to go to the last of this talk and talk about the challenges and opportunity, because I only have 10 minutes left. In fact, my time is up, but is it okay if I take 5 more minutes?
Yes, please.
Okay, so there are like, what are the challenges and opportunities? So as far as application is concerned, we have explored so far physically unclonable computing for PUF and logic locking. We have done side channel obfuscation for instruction level obfuscation of power side channel. We have done random number generator, both pseudo random and true random. We have done what is the other? We are now developing an encryption algorithm, image encryption algorithm. what is the other? We have done reconfigurable and flexible computing. So there are quite a few applications we have explored, and we have reported that in our papers. So we have shown proof of concept. Now, to make this thing an actual reality, right, in a technological reality, what are the main challenges? The main challenge is that portability. Like the first main challenge is portability. So analog circuit design is not like digital design. You write a Verilog code, it is portable across technology node. You go from 45 nanometer to 22 nanometer, doesn't matter. With our analog circuits are very, like the dynamics is complicated. So if you just take the topology and implement it in 22 nanometer by scaling the dimension, it will not work. We have tried it, it doesn't work. So for each of this technology node, you have to kind of reinvent the wheel and use that analog circuit design intuition and it takes time, to do that. Even after years of experience, it still takes time. So to make, but the reason semiconductor industry is so good is that we reduce the transistor size, technology continuously advance. So if you design something, it has to be redesigned every 2 years. That's the problem, right? So that's the problem, portability. Scalability is a big problem. So, same kind of idea that if you scale it down and different application, for each of them, you have to separately optimize it. It's a huge headache. Robustness is a big problem of analog circuit in general. So PVT variation, noise, and all that. So that has to be more rigorously studied and theoretically, experimentally, and by simulation. So that's a big challenge. Evaluation, like how do you evaluate a chaotic system? So I have to show a slide to kind of emphasize this, is that this is from one of our papers, right? How do you evaluate a chaotic system? There are 2 dimensions. Actually, there are 3 dimensions. So first dimension is the performance as a chaotic system. So for that, we have the quantity, which we call the chaotic ratio or CR, the quality, which is the Lyapunov exponent, average Lyapunov exponent or ALE. So this is chaotic performance, right? And there is a bunch of other metrics as well. I'm not going to go into that. But these 2 basic things like quality and quantity of chaos. Yeah? So we have to measure that. But also for edge computing, we have to be mindful about the overhead. And at least the 3 main things like area, speed, and power, we have to consider them. So we proposed a figure of merit based on that. So we want high chaos, but low overhead, basically. Okay, so that's the challenge, that how do you evaluate things? The robustness part, we have not yet thoroughly analyzed it. Robustness is the PVT variation or noise immunity. So that has to be included as well in the fold. So these 3 domains of evaluation. So chaotic performance, system level overhead, and then the robustness. And somehow they have to be, we wrote a paper on kind of the preliminary work on this, but a lot more needs to be done. And then the application is space exploration. I just talked about like 5, 6 applications that we have been working on. So we need to optimize the design for each of these applications. Not necessarily the same design is good for all applications. So that's a lot. So in summary, all the 5 challenges, if I summary, the last part is design and optimization, basically. It's the design and optimization problem. So what we are now looking into, and I'm very excited about it, is that how can you use the current boom in machine learning? So basically, how can you use the machine learning knowledge in EDA, electronic design automation of this chaotic system? There has been a lot of interesting work, mostly focused on digital systems because that's the most popular thing. But even in the analog domain, recently, deep reservoir computing has surprisingly has had amazing success. I mean, not amazing, I would say, but very interesting success. So we are now looking into that. So there have been work from Berkeley and other universities, a few other groups who have been working on this. So we have been looking on their work. They are, of course, focused on traditional analog circuit like amplifiers and so forth. So we are looking on their work and see if we can build on this to come up with a optimization framework. So there will be 2 aspects of this. Like one is optimizing existing topology, and then a generative AI, which will bring you new topology, on optimizing. And how much should optimization? So what will be the cost function? So that's something we are looking deeply at. Like, should we want to implement the objective function? Should it include chaotic performance plus overhead plus robustness? So it will going to be a very complex optimization like objective function or cost function. So how to kind of modify the deep reinforcement learning to that. So that's something, it's a very challenging problem, but we're looking into it and I'm excited about next year. So maybe we will be able to make some headway into that. There have been some other methods of doing this. So people have done, Dr. Forte from University of Florida, their group has done a work on evolutionary optimization and Bayesian technique to optimize this sort of chaotic circuit. So there are other methods possible as well. So we are looking into different machine learning techniques, which one will be more appropriate for kind of solving these challenges and opportunities. And of course, there must be other ways to do this. So people should explore. So that's my challenges and opportunities. And finally, I have provided a list of our recent papers. So we have 23 peer-reviewed publications. Given this list, you can check out for more details, which I could not cover due to the constraint of time. And finally, a concluding thing. So this I always say at the end of my talk is that traditional engineering has focused on linear systems. Nature is nonlinear, and the full extent of the complexity cannot be appreciated without taking this into account. Chaotic system has nonlinear and chaotic system has become interesting among mathematicians and physicists and some of the engineers, but it's still a vast uncharted territory waiting to be explored. So it's an exciting field for today's electrical engineering and computer science graduates. I invite the audience to take part in this journey to unravel. So there are two parts: unravels nature's mystery. So that's the scientific question. And then also the engineering portion of building next generation secure computing system. So with that invitation, I am concluding my talk. If there is any questions, I'll be happy to take.
Thank you, Dr. Sakib, for the great presentation. I think Jameson can look at all the Q&As as it comes through, but I can start the first question. Yeah, I think, this seems like, interesting new area, emerging area, looking at, looks like you mentioned about, the goal here is the optimizing, overhead, energy trade-offs, and, and understanding different chaotic systems, whether it's 1D or 2D or 3D. And when you talked about bifurcations, could you help me in connecting why you treat them as three different systems from an engineering point of view? What do you mean by, what does it mean for a system when you say left bifurcate, right bifurcate? Could you shed some light on that?
Sure. Yeah, let me go back to the slide. Yeah, so basically what we mean by that is that I put too many slides, I think. Let me just do this. Yeah, so I think you are talking about this slide.
Yes, yeah. And you mentioned that each one of them you're treating in this work as a system. So I'm just curious, what does that mean? The assumption of left bifurcate means in terms of, does it emulate a particular condition or scenario in terms of, or within the chaotic condition?
No. It's just like a mechanics of the thing. So there is no fundamental thing about this. It's just that when we implement things in systems, so our basic, let me just show the basics. So this is more of an engineering challenge, nothing like
Sure. We understood this one. So
so basically, yeah. So basically, what we try, our main like big top design principle is like this. So we have seed map X and seed map Y. So these are all, let's say, 3 transistor circuits, right? And what we are trying to do is that seed map Y has chaotic operation between, let's say, 0.5 and 0.7, and X is between 0.2 and 0.3. So we use a nonlinear transformation so that this output projects to the chaotic of X and X's output projects to of Y. So basically the design part, we have to come up with these two blocks, nonlinear transformation block, so that it projects into the chaotic region, right? So when we try to actually do this, so take this big, like top higher level idea to implement in actual circuits, we found out that the main challenge is that each of these seed maps has different bifurcation region, you know. So the nonlinear transformation circuit has to be separately designed depending on your projected goal. So if your projection goal is here, right, between 0 and 0.25, it has to be one type of circuit. If the goal is between 0.3 and 0.7, it has to be another circuit. Between 0.6 and 0.1, it will be. So you see, like that was the thing. So there is nothing fundamental about it. It's just the design.
Sure. Threshold classification. Okay. Anyway, so the second question I have is, what is your take on? I understand this all has to do with this so-called coming up with logical constructs, for at the circuit level. How do you draw similarities between quantum circuits versus the chaotic theory-based thing? Are these two relatable, or are they two distinct, or how do you see? Because it looks like this is also not there yet, and quantum is also not there yet, but I think but are there any, there are many applications of cybersecurity when you talk about key size generations or secure communications or network security, where we all want those randomness, we all want those ways to have a deterministic and yet have a fully reduced overhead and still that. So I'm just curious to see, how do you draw conclusions between these two domain, between quantum circuits and chaotic theory, and the logical construct. The ultimate goal is to come up with this logical construct. Somehow it's puffs, or so I'm just curious to see where exactly it is standing right now in terms of the size. The qubits are, IBM says, about 1,000 qubits, and then I'm looking at, in the miniaturization level of or realizing some logical construct, and how do we, what is the size limit in terms of these two systems? And any input on these two? I know I'm throwing up a very big picture between these two, but I'm just curious to ask your opinion.
Right, right. I mean, this is such a good question that I don't like. How much time do we have? Like, you go to the exact fundamentals of this. So, basically, how can you harness unpredictability? Quantum computing can do that. Chaos computing can do that, but they are fundamentally different approach. Like from a fundamental physics perspective, they're fundamentally different. Quantum is actually more mysterious, I would put it some other way, because we don't know actually all the answers. In chaos is surprisingly simple and is still unpredictable. So it's actually a deterministic system. So we know the equations and we actually can reproduce it, but it still seems like unpredictable, So there are two fundamental approaches and they're so deeply tied. So I'm going to take a detour into physics to shed light, like shed one part of this, is that there was this dream of Newtonian mechanics that if we know the equations, so nature is written in terms of differential equations. If we know all the differential equations and we know the initial condition, then we can predict nature into the future. So that was the dream of Laplace, the Laplacian demon. So there was the overarching thought of the scientific community until the first part of the 20th century, when modern physics came up with quantum, like theory of relativity and quantum mechanics. Quantum mechanics was very surprising because Heisenberg's uncertainty principles tells us that we actually cannot measure like two things simultaneously, like velocity and momentum. But it's in general, like position and momentum is not just the thing. I mean, it's just any two very distinctly related things. It's a fundamental limitation of the nature, apparently. Like it's not about our measurement system. Like even if we improve it to 100,000%, it will never be able to exactly measure two things at the same time. So that was the first blow into that mechanistic worldview, that world is predictable. And the second blow is the 1963 Lawrence paper, is that first of all, we learned from Heisenberg principle that the initial condition, our sensors will never be able to measure the initial condition 100%, right? But it was only a very tiny fluctuation, right? If you make very good sensor, you know almost exactly the initial condition. And people thought that, okay, but in reality, what does it matter, So the system will be almost predictable. What Lawrence showed is that no, if you have even the tiniest of fluctuation, if the system is chaotic, you can predict until 20 iteration, 200 iteration, 2000 iteration, highest. After that, things will diverge. Your prediction will not match. That's why we cannot predict weather. We have all this phenomenal technology, but we cannot predict weather. That's why climate prediction is so difficult. Like it's a chaotic system, nonlinear chaotic system. So you can predict up to 1 week pretty well. If you want to predict up to 2 weeks, it needs exponential increase in resources. After that, you need another exponential increase. So this is called the event horizon of prediction. Or I'm probably messing up the term, but you see what I'm saying. Like there is a prediction window after which things diverge. So combined with that quantum mechanics and chaos theory, actually, like it fundamentally changed the outlook of the physics community. That is actually reality predictable, like we are nature predictable. So and that brings to your question. Like actually, these two things, I am very surprised. Like this is the first time I have this question. Like these two things are so different that nobody related those two things. Okay, so actually there is a fundamental connection between these two things, and for the quantum computing part, to be honest, like I don't know enough about quantum computing. Like what's the state of the art, what people are doing, and the physics is rather complex. So I cannot say like where the state of the art is. I heard interesting things. There are like a lot of buzz about quantum computing. What I know is that you need cryogenic or almost very cool environment. So it's not feasible for edge computing, if I understand it correctly. But maybe for data centers and like big data centers, you can do that. Yeah, so that's I mean all I can
Thank
say.
you. Yeah,
Yeah.
thank you. Sorry for putting you on the spot, but I think you're right. I think we're working on different projects and proposals in quantum with other institutes. I think I'm seeing some connections, but I still didn't understand both in a complete way in some sense. But anyway, we'll
No,
leave it
thank
to
you,
that.
thank you. I mean, this is a very interesting question.
Yeah, let's see whether others have any questions. Jameson, do you see any questions? Or
Yep. Narupa asks, one moment.
I mean,
Narupa,
can you turn on the video? I mean,
oh,
can
yep. Sorry about that. Narupa asks, will the assumptions behind the Lyapunov exponent change when applied to quantum computing applications?
Sorry, can you repeat the question?
Yes. Will the assumptions behind the Lyapunov exponent change when applied to quantum computing applications?
Oh yeah, I mean, I have no idea. I don't think Lyapunov exponent, the idea of Lyapunov exponent, as far as I know, is not applicable to quantum system. So Lyapunov exponent is strictly an idea about chaotic dynamics. In fact, not just chaotic dynamics, like nonlinear dynamic system. So it comes from the theory of nonlinear dynamic theory. As far as I know, it has got nothing to do with quantum physics.
Okay, thank you. Then our next question is from Mira. How do you plan to incorporate machine learning and artificial intelligence techniques in conjunction with discrete time chaotic systems, especially in conjunction in the context of random number generation within edge computing environments?
Yeah, so that's the dream. So in my challenges and opportunities, by the way, can you enable my video? I cannot turn on my video.
Oh,
I cannot turn on my video.
no, I can allow you.
Yeah, I think
I
at this
can-
stage, it would be nicer to. Yeah, thank you.
Yep.
So yeah, so I think that was a very good question. And in fact, that is my primary focus right now. I'm actually collaborating with another researcher in this field. And we're trying to address this problem. So what are we looking into is that we have all these big challenges, like opportunities of analog chaotic circuit, discrete and chaotic circuit, but it provides so much challenge, the portability problem, scalability problem, robustness problem, evaluation problem. So basically the design and optimization is a huge space, and so far we have been doing proof of concept system, like small systems for small application. And yeah, I mean, we can do that manually with our kind of analog circuit design hat on. But when it actual big system and optimizing, juggling between so many different vectors, it just is not feasible. So we need some sort of learning algorithm to do it for us, some sort of optimization technique. So fortunately, there has been this revolution in artificial intelligence, especially neural networks, in the last 10, 12 years. So we are looking into different techniques people have tried in similar domain. So far we have identified 3 promising avenues. So there have been some work with evolutionary optimization, Bayesian theory, naive Bayes, and reinforcement learning. Among them, to me, at least right now, deep reinforcement learning seems to be the most promising avenue for analog circuit design. But yeah, so the goal is that first defining the objective function, the cost function, what is actually we're trying to improve. So we need to have a measure for the robustness, measure for the chaotic performance, and measure for the overhead. And then based on we properly defined objective function, we have to adapt and we have to learn deep reinforcement learning. So I don't have a background in machine learning. So that's the challenge. So preferably, we'll collaborate with people who are more, or maybe we just learn it now. But either way, the main thing is that like how to define the cost function. What are the advances that have been made in the field of machine learning for circuit design? Take those ideas with our circuits, throw our topologies into the machine, and it will come up with an optimized circuit, right? Which solves for a particular application space. Our more ambitious goal in this domain is generative AI. So right now we are coming up with this new topologies based on our analog circuit design insight and chaotic system insight. If we show enough examples, so we already have we have proposed 17 or 18 new topologies so far in the last 6 years. So we have a bunch of examples and a lot of data. If we show it to a machine learning algorithm, can it come up with a new topology that we never thought of? So that would be the holy grail of this machine learning thing, that when we be able to optimize, not just optimize existing topologies, but generate new topologies. So that is the ambitious goal. So we have started a collaboration recently and working towards it. So hopefully there will be some updates in the next 2 years.
Okay, thank you. And then our last question from Tanzim is, some chaotic systems are known to be vulnerable to various attacks. What are some ways to safeguard chaotic systems against common attacks?
Yeah, there are several attacks. So one thing I mentioned earlier is that 1D chaotic system, because their dynamics is limited, can be used machine learning attack. So there have been some machine learning attacks on that system. So that's why we have moved on to higher dimensional maps, like 2D, 3D. We have so far only done 2D, but we are currently working on a method which should extend it to arbitrary dimension. So ND, so 3D, 4D. And each of these, the complexity goes exponentially. So it makes it exponentially more difficult. Again, it's an arms race in security. So whatever we come up with, attackers will come up with something, and then we have to up the ante. So yeah, we are working on that.
Okay. Well, thank you for your presentation. You'll be receiving a plaque and a certificate of appreciation from the Center for Cybersecurity Research. Also, we just verified that you'll be giving another presentation in March. So we're looking forward to that. And I'm sure we'll stay in touch. Thank you.
Thank you so much for this kind invitation and the opportunity. I'm going to share the slides with you and the links of my previous presentation on this topic, which are available in YouTube. So the interested audience can explore.
Thank you. And we'll share the link to the YouTube video shortly.
Sure. Thank you.
Yep.
Thank you.
Bye.